Okay. Okay. Sorry for change the schedule of for our class because I could not uh, make it for tomorrow afternoon. Okay. Because I send my second son to his boarding school at Segamat. Okay. So we will have 2 hour class and tomorrow we will also have 2 hours. Okay. So I try to complete all the syllabus where belong to my part. Okay. Okay. For today, we continue for the finite slope. Okay, where we discuss on the use of chart. Okay. So from the previous class, I have discussed on the total stress approach. Okay. Uh, then before that, we discuss on the linear failure plane methods. Okay. So now we discuss on the use of the chart, and then we may continue with the method of slices. Okay. So there are several chart has been developed, okay, by several previous researcher, okay. For example, Taylor stability number, okay, Jumbo stability chart, and then we have Bishop and Morgenstern chart for effective size analysis, and the last one that I refer is the Morgenstern graph for rapid drawdown. Okay. However, we only discuss on the Taylor stability chart for this course. Okay. Okay. So basically, this is the chart. Okay. And there are another chart. Okay, that's been developed by Taylor as well. Okay. So based on this chart, okay, there is this is what we call as the stability number. Okay. So this is we call as stability number. Okay. So all of the chart, okay, we can consider as a dimensionless approach or normalized approach. Okay. So for example, for the stability number, it's just a number without any units. Okay, where the gamma times h over c. Okay. Gamma is kilonewton per meter cube times h meter over c kilonewton per meter square. Okay, so beta is considered as a degree, so it doesn't have any units. Okay, then this curve or this line, okay, it is related to what we call as to phi. Okay, also doesn't have any units. Okay, while for this last line, okay, so this is dedicated for the phi zero equal to 0. Okay, where it separate the line into several ND value. So ND is the h over h. Okay, the distance or the height of what we call it of the slope. Okay, and the height from the toe to the what we call as to the hard rock or bedrock or hard layer. Okay. So it has 1.2, 1.5, 2.0, 4, and until infinity. So before we look on the chart in detail, okay. So I just want to share with all of you, okay, regarding on how Taylor developed this what we call it this chart by using a dimensional analysis. Okay. Okay, actually I have shared before you join. I will share again. Okay. Uh, Okay. So this is a dimensional analysis. Okay. I will brief a little bit, okay, because it's very useful tools, okay, methods where you may use, especially for your master by project, or if you are further your PhD, or if you want to use it for your for uh, for, uh, for your career, okay, so you can make use of these methods, okay. So it calls a dimensional analysis, okay, or some reference book call it is as Buckingham Phi Theorems. Okay, so dimensional analysis is a method for deducing elements of the form of a theoretical relationship from consideration of the variable and parameter that make up that relationship. Okay, so okay, we want to get all the important element, okay, which is considered as variable and parameter, okay, that make up this all any relationship uh, related to any problems that we want to investigate. Okay, so it should based on a theoretical approach. Okay, so we need to refer for any theoretical concept. Okay, uh, to solve which is related to the problems. Okay. So dimensional analysis of problem then lead to a reduction in number of variables that must be studied in order to understand the problems. Okay. So once we already obtain all the important parameter, so we can reduce the number of the variable that we want to investigate. Okay, for example, due to the time constraint, due to the limited budget. Okay, so we want to focus only for several parameter, and definitely where this parameter has not been investigated well by all or any previous researcher. Okay, the key is to create dimensionally homogeneous equation whose form does not depend on the units of measurements. Okay, so the output or the objective of this dimensional analysis, okay, we want to create, okay, a dimensionless equation. Okay, so governing equation cannot just be plucked from the air. They must come from an underlying insight into the phenomenon that is being modeled. Okay, so it means that we need to understand the fundamental of the problems. Okay, so in order to understand it, so we need to refer for the uh, for the for the background of the problems, or from the theoretical uh, view from which is discussed on that problems. Okay, the theory of dimensional analysis is encapsulated in the Buckingham Phi Theorems. Okay, so Buckingham Phi Theorems state that if there are n variable, okay, so this is the number of the parameter in a problem, and this variable contain m number of primary dimension, for example mlt or flt. Okay, the equation relating all the variable must will have n minus m dimensionless group. Okay, so for example, if the variable is 8, okay, from each variable, okay, so we obtain the primary dimension for each variable. Okay, so then for example, if the m is equal to 2, okay, so 8 minus 2 it becomes 6. So we need to create 6 dimensionless equation. Okay, I will show later on, okay, from several example. Okay, so Buckingham refer to this group as 5 groups. Okay, so the 5 group must be independent of each other, and no one group should be formed by multiplying together power of other groups. Okay, so it should stand alone. Okay, so it cannot relate from the other what we call as dimensionless equations. Okay, So this method offers the advantage of being more simple than the method of solving simultaneous equation for obtaining the value of the indice. Okay. So this method is more easy or more simple compared to any other methods. Okay. So in this method of solving the equation, there are two conditions. Each of the fundamental dimension must appear at least one of the m variable. Okay. It must not be possible to form a dimensionless group from one of the variables within a recurring set. A recurring set is a group of variables forming a dimensionless group. Okay. So we should use one on in when we derive the dimensionless equation. Okay. However, we can reuse it again. Okay. For example, any parameter. Okay. If we not use the same parameter, we could not provide or could not solve for the last dimensionless equation. Okay, I will show it in the example later. Okay. Okay, fundamental quantities most commonly employed are based on Newton's second law, okay, which state that the rate of change in momentum of a body is proportional to the applied force. Okay, so this gives force proportional to change of momentum over time. Okay, so momentum equal to mass times velocity. Okay, and acceleration equal to velocity over times. Okay, so therefore force equal to mass time acceleration, which is F equal to ma. Okay, so this is based on the Newton second law. Okay, so making unity of the constant value, the relation above is expressed dimensionally with give F is the force, m is the mass, while the accelerations is equal to meter over time square, or L multiplied with t power by -2. Okay, so F is the force, m is the mass, L is the length, while t is the time. Okay, so the equation relates four dimensions where F, L, and T. Okay, so therefore L and T is the fundamental dimension required for geometry in kinematic. Okay, the third fundamental dimension is dynamic. Okay, can be either force or mass. Okay, so we have here L geometry, T kinematic, and then we have force and or mass. Okay, so it means that either we can use FLT or we can use MLT. Okay, so the choice of this quantity depends upon the measuring system, whether to employ MLT, which is based on the SI system, or the FLT, which is based on the British system. However, in this work, since mass is the fundamental physical quantity, the latter are employed in deriving the dimension value of the equations. Okay. So it depends. Okay, for example, I prefer to use FLT, okay, because in geotechnique, we have a lot of parameter which is refer to force. Okay, so if we are using the MLT, so we need to change the force into mass. Okay, so then we have a T. So actually T is not time is not the less number of the primary dimension. I guess that 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 will be the best. Okay, so in that case, it is better to use FLT compared to the MLT. Okay. So selection of the relevant independent parameter can be quite difficult. The resolution of related problem requires sufficient experience. Okay. So actually, it depends on what is the interest of the researcher. Okay. So for example, if he or she want to look more on, for example, parameter A, okay, most probably there will be a lot of parameter A in some of the equations that has been derived. Okay, for example, if he or she want to investigate more on parameter B, okay, So he or she will develop a lot of experience, a lot of equation related to B. Okay. So dimensional analysis with Buckingham Phi Theorem provide useful hint in determining the various factors that involved in the analysis and the relevant data to be collected. Okay. So we look on some of example. So I guess from this example, you can better understand on these Buckingham Phi theorems. Okay. So for example, of the factor of safety, Fs, of a slope formed in purely cohesive soil. Okay. So factor safety is the output. Okay. So in deriving the equation, so we should include the output and also the input. Okay. For example, the output is factor safety, while the input is H, theta, Cu, gamma, and V. Okay, so we have here Cu. Okay, and then we have gamma. Okay. Purely cohesive soil, so it means that it doesn't have any phi value. Okay, so theta is the angle of the slope. Okay, and then we have H and also D. Okay, so in total, okay, the output, the input is 5, 1, 2, 3, 4, 5. Okay, and then include with the output, it becomes 6. Okay, so n is the number of the parameter involved. Okay, so n is equal to 6. Okay, so then from each parameter, okay, so we should determine what is the primary dimension. Okay, so for example, for the factor safety, it doesn't contain any units, so we just write down as 1. Okay, and H is equal to meter or length or geometry, so we write as a L. Okay, while theta is a degree, so it doesn't have any primary dimension, so we write as 1. Okay, Cu is the kilonewton per meter square. Okay, so that's why it is preferred to use the FLT rather than MLT. Okay, so for the FLT, for the Cu, so it will become F is the force, okay, kilonewton, okay, times L power by negative 2, okay, which is kilonewton per meter square. Okay, then we have a gamma. Okay, gamma is kilonewton per meter cube. Okay, so F is the force times L is the meter in cube. Okay, so F times L power by negative 3. So then we have here D. Okay, so D is the meter, then it become L. Okay, so we need to count how many primary dimension in this derivation. Okay, so L is 1. Okay, 1 is not considered as a primary dimension. So then we have another one, F. Okay, so so this is still L. Okay, so we do not count because it already count. So we have 2. F is already count. L. So it doesn't contain of T. So the number of the M is equal to 2. Okay. Okay. So later on, 6 minus with 2, it become 4. So we need to derive 4 dimensionless equation. Okay. Okay. So first we to make it simple and easy. Okay. So we derive the dimensionless equation first. For example, Fs, okay, it doesn't have any dimension. Okay, theta, okay, so we already derived 2. Okay, okay, so then we already derived 2. Okay, so then we have 1, 2, 3, 4. Okay, so we need to develop two more. Okay. So another simple way is to use meter, okay, by meter. Okay. So H over D or D over H. Okay. So we have the third one. So then the last one, okay, is to use Cu and also the gamma. Okay. So in this case, we need to use either H or D in order to get a dimensionless equation. Okay. So it is allowed to reuse any what we call as any parameter. Okay. Due to we want to construct for the last dimensionless equation. Okay. So Cu over gamma times H is the last dimensionless equation because I not put in order. Okay, so I just want to explain. Okay, first we need to consider for the dimensionless equation first. Okay, and then we derive the simple one, and the last one we try to solve the remain parameter. So for this case, Cu and gamma, so we need to add either H or D. Okay, so in this case, look like H is most important for the researcher. Okay, so in that case, okay, he referred to H, okay, as the main concern from his investigation. Okay, so from this parameter or equation, later on, okay, he has developed this kind of equation or chart. Okay, so this is what has been developed by Taylor. Okay, the stability number. Okay, so this is stability number developed by Taylor. Okay, okay, so D over H. So it means that any other researcher that want to use or want to validate his analysis, okay, so he or she can easily refer to this chart, okay, without worried on the geometry of the, for example, testing chamber or the geometry of the slope, okay, because you already use the normalized approach. Okay, so this is for the slope. Okay, so this is for a fault cone. Okay, the fault cone used as a quick measure of undrained strength in the laboratory. Okay, where it has D, the penetration depth. Okay, W is the width of the cone. Cu is the undrained shear strength of the soil, while alpha is the apex angle of the cone. Okay. For example, for a liquid limit test, okay, the value for the mass is about 80 gram, okay, and the angle of the cone is about 60 degree, okay, and the penetration depth is about 20, okay, millimeter, okay, and the Cu, if you're not mistaken, okay, for the liquid limit condition is 1.78 kilopascal. Okay. Okay. So this is the important parameter, okay, for the Falcon methods, okay, in determining the undrained shear strength of the soil. Okay, so we have four. So from the four, for each dimensional, for each parameter, so it contains two, the primary dimension. For example, D is L, W is F. Okay, actually M is referred to W when we multiply M with G. Okay. So Cu is the undrained shear strength, while alpha is the angle. So alpha doesn't have any units. Okay. So from there, 4 minus 2, it becomes 2. Okay. So first we use the alpha. Okay. And from this equation, so we need to derive, we need to use all of the equation. Okay, so Cu kilonewton per meter square, okay, times d square, so it become kilonewton, over W, so it become dimensionless. Okay, so that is for the four-core method, and this method has been used or has been developed by Wood and Rowe from Oxford to determine the what we call as plastic limit of the soil by using the four-core methods. Okay. Bearing capacity of soil. Okay. So for the bearing capacity of soil, okay, PU is the load, okay, because it is a capital PU, it's a capital P, okay. So this is the output, okay, while L is the length of the footing, okay. Then we have B here, B is the width or breadth of the footing. So then we have D is the depth of the footing from the ground level, okay. So then we have CU is the strength of the soil, okay. We have here phi, okay, is the internal friction angle, and the last one is the unit weight gamma. In total, we have 7 parameter, okay. So from each parameter, we derive the primary dimension, and then we have 2. Okay. So from there, we derive the dimensional equation. So we need to have 5 in total. Okay. So 5 is a dimensionless. So we need to write 4 more. Okay. So we need to make sure that we use all the what we call the equations. Okay. For example, L over B. Okay. Then we have D over B. Okay, so the rest is PU kilonewton over gamma B square L, okay, and then CU is over gamma times B, okay. So it looks like the researcher is more interest on the B, okay. So this is B, L over B, D over B, and B, okay. So the last one is the vertical cut, okay. So for vertical cut is the output is the factor safety, okay, while the rest is the what we call as the input, okay. So we have alpha, H, gamma, Cu. So the total number of the parameter is 5. So from there we derive the primary dimension and then we obtain 2. Okay, so we need to develop 3 dimensionless equation. Okay, so we have Fs, we have alpha. Okay, so then the last one should be the use of the gamma, Cu, and H. Okay, so the last equation is Cu over gamma H. Okay, so that is for the dimensionless equations. Okay, so I guess you can make use of this method, okay, in your master project or in your uh, career, or you may use for your work, okay, at the office. Okay. Okay.
The point.
Ah,
Is
you?
this the same method for your PhD also?
Yes, yes, yes. Yeah, actually, I use this kind of approach, okay, to identify what is the important parameter, okay. Then I'm focusing on several parameter which is not been considered by any previous researcher, okay. And also I develop a dimensionless graph, or what we call a preliminary design chart, okay, by using a normalized or dimensionless approach, okay. So it's now we have what we call as a software, so it will be easy to carry out for a parametric study, okay, by change the geometry or change the soil properties value, okay. then we can develop what we call as a dimensionless design chart. Okay. For my case, I run more than 2,000 analysis by using a software and then come up with the dimensionless design chart. Okay. Okay. Okay, now we look for for the example okay, on the use of the Taylor design Taylor chart. Okay, so we go for Dr. Noli Gofar reference book. Okay, and then later on we look on Dr. Kamaruddin reference book on the use of this dimensionless on Taylor design chart or Taylor charts. Okay. So there are many chart. Okay, the most popular is one is the Taylor stability number. Okay, other chart. Okay, Taylor chart 5.8 can be used to evaluate stability of the slope in a homogeneous cohesive soil with a hard stratum at the depth of ND over H from the surface of the slope. The factor safety can be calculated as. Okay, so this is stability number. This is stability number. While this is the factor safety. Okay, so the example from Dr. Noli, okay, she used the equation of 5.26, okay, to obtain the standard number, and at the same time, she also used the try and error methods, okay, to determine the factor safety value. Okay, okay. The first example, okay, a cutting in the cohesive soil form a slope angle of 35 and height of 8 meter. Okay, the undrained cohesion CU is 14. The unit weight gamma is 18. Okay, so it doesn't have any phi value. Okay, so the phi is equal to 0. Okay, using Taylor stability number chart, determine the factor safety against shear failure for a hard stratum exists below the slope. Okay, and B, a hard stratum, okay, exists at 4 meter below the toe. Okay. So for the first case, okay, so we have here Cu, gamma, T is equal to 0, beta is equal to 35. Okay. So ND is equal to infinity. Okay. Okay, from the chart, and S is equal to 5.52. Okay, so we look on the chart first. Okay, so this is the stability chart. Okay, first we need to determine what is the beta value. Okay, for this case, the beta value is equal to 53. Okay, so then because in this case the P is equal to 0. Okay, so we need to determine what is the ND value. Okay, so the ND value, okay, is the ratio between height, what we call, sorry, the height from the toe to the heart stratum, okay, and also over the height of the slope. Okay, so for this case, okay, okay, the ND is equal to infinity. Okay, a hard stratum exists well below the slope. Okay. Okay. I'm not sure why the author use equal to infinity. Okay. Because he mentioned here that the hard stratum is rest below the toe. Okay. It's supposed to be h over h. Okay. where h over h is equal to 1. Let me read again. 12. Okay, the height is 8 meter. Okay, a height stratum exists well below the slope. Okay, the height stratum. Okay, for example, for the B, the height stratum exists at 4 meter below the toe. Okay, so if 4 meter below the toe, definitely, okay, the value of ND, 8 plus 4 is equal to 12. Okay, so from there, the H is equal to 8. Okay, so from there, we can obtain 1.5. Okay, so that is reasonable. That is reasonable in terms of the definition and the value of ND. Okay, but for this ND, okay, the author has put ND is equal to infinity. Okay? For example, NDH is equal to 8, okay, plus 0. Okay, so because height stratum exists well below the slope. Okay, so if NDH is equal to 8, okay, then we divide with the 8. So ND is supposed to become 1. Okay. That's why I'm not sure why he state ND is equal to infinity here. Okay, let's see if it is equal to infinity, okay, unless the height strata exists far below the slope. Okay, so we can consider as well is refer to far.
So can we assume that it's equal to 0 when they say like the height stratum exists well below the slope, as in there's no value for h?
Do you mean the NDH is equal to 0?
Because if you look at the formula down there, it's ND equals to h over h, and the h is the height until
This is the
stratum.
height.
The height until stratum,
This
right?
is
Height
no
until
no
stratum.
no. His is the height of the slope.
Oh, okay. And then the okay.
I guess it's far below the slope. Okay. Okay, so okay. Now let's say if we assume it's infinity. Okay. So from this stability chart, okay, a number, okay. So 35, okay. And then we draw a line, okay, straight to the infinity, okay. So then definitely the value is equal to 5.52, okay. So if 5.52, okay, then we can get the factor safety from the equation 5.26, which is equal to 1.53. Okay. Okay. Because why it is straightforward. Okay. Without using any try and error. Okay. Because the fee is already 0. Okay. If we use the FSC or SFP value, which is the one that we have discussed previously, so it still become the same value. So that's why means that the FSC or FSP still become same if we use different factor safety. Okay, so in this case, the author use straightforward equation which is equal to 1.53. Okay. So the second one, height stratum exists at 4 meter below the toe. Okay. So NDH, okay, is equal to 8 plus 4. Okay, because the height of the slope is 8, while the 4 is the height stratum. Okay, so it's equal to 12. So then 12 over 8 will become 1.5. Okay. So where we look on this diagram, 1.5 is this curve. Okay. So when the value of the what we call it of the beta is equal to 35, okay, so we draw a straight line until it meet the 1.5 here, so it will become 6. Okay, so ns is equal to 6, so then ns 6 times 4 over 18 times 8, it become 1.65. Okay. So that is for the okay. Okay. So the second example, determine the factor safety in terms of effective strength for the slope with beta is equal to 40, the height is equal to 10. If the properties of the soil are follows, C is equal to 20, Phi is equal to 10, gamma is equal to 17. Okay. So Phi is equal to 10, beta is equal to 40. If we look on the stability number, beta is equal to 40, Phi is equal to 10. 40. So the value of the stability number is around 10 point something, 10.7. Okay. So from this 10.7, okay, the factor safety is equal to 1.26. Okay. So that is for the example 5.8. Okay. So 5.9, okay, a little bit different, okay, where she used the try and error. Okay, I just wondering why for 5.8 she doesn't use the try and error methods. Okay, because in this case the phi has a certain value which is 10. Okay, okay, then for the 5.9, okay, determine the factor safety for the slope with the height of 5.5 meter and the slope angle 40. Okay, the unit weight of the soil forming the slope is 16.5, while the shear strength parameter of the soil is C is equal to 20 and Phi is equal to 10. Okay, so for beta is equal to 40, Phi is equal to 10, H is equal to 5.5, and gamma is equal to 16.5. Okay. Okay. So she sorry, the author used uh the 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 factor safety is equal to 1, okay, to begin with. Okay. So when we use the factor safety of 1, okay, definitely the same Phi that we use is 10. Okay. So from the chart, okay, when the Phi is equal to 10 while the beta is equal to 40, so we obtain 10.7. Okay. So from the 10.7, okay, with the use of C is equal to 20, okay, so then we obtain the factor safety is equal to 2.36. Okay. So this 2.36 is not equal to what we call as the factor safety of 1. Okay. So then she increased the factor safety value of the Phi. Okay. So then from the phi d, okay, she obtained 5.6. Okay. So from the 5.6, okay, uh, due to the chart doesn't have the value for 5.6, okay, to be exact. Okay, so in this case, she used the interpolation method. Okay, so from the interpolation, when she interpolate, okay, to determine the phi d equal to 5.6, the ns is equal to 8.324. Okay, so we look on the chart, for example, there is no 5.6. Okay, but actually we can just guess. Okay, for example, if the beta is equal to 40, Okay. So beta is equal to 40. So, okay. So we just guess around here. Okay, about the value for the 5.6. Okay, and then we try to get the value of the stability number. But the best way is to use the interpolation. Okay, get the value for the phi equal to 5 and the phi is equal to 10. Okay, so from there we can estimate the 5.6. Okay. So then NS is equal to 8.324. Okay, by using the C is equal to 20. Okay, then they obtain the value for the factor safety is equal to 1.83. Okay, the value means that the factor safety of the phi is equal to factor safety of the C, which is 1.8. Okay. So the 5.10, okay, determine the safety factor for a submerged field with a height of 30 meter and the slope angle of 30 degree. The saturated unit weight of the soil is 19, while the shear strength parameter of the soil are C is equal to 35 and phi is equal to 5. Okay. So by using the factor safety of 1, okay, so she obtained 9.25. Okay. So then she used the 9.25 and with the rest parameter. So then she obtained 1.17. Okay. So in this case, she assumed that FSV is equal to FSC. Okay, because 1 equal to 1.17. If 1.17 round out to the nearest decimal number, one decimal number, so it become 1.2, or without any decimal number, it become 1. Okay, but for me, it's better to continue and then we plot the graph. Okay, and then check the relationship between the FSV and FSC with the unit line of equality. Okay. So for me, it's better to look on Dr. Kamaruddin approach, okay, which is much more easy to understand, and we feel that it is more appropriate to be used. Okay. So this is the way that Dr. Kamaruddin explained for the stability analysis of finite slope using Taylor chart. Okay, so this is the procedure. Okay, actually, what has been discussed with Dr. Nudi is a little bit similar with Dr. Kamaruddin, but Dr. Kamaruddin explained more detail. Okay, okay. So first, assume a factor safety in terms of internal friction angle, FSP. Okay. So then determine the mobilized internal friction angle, phi r, okay, which is we include the factor safety phi, okay, to get the phi r. Okay. Okay. Then we refer to Taylor chart, okay, to obtain the NS. Then determine the mobilized cohesion, okay, from the NS value, okay. So this is the CR, okay. So from the CR, the C, the actual C divided with the CR is the FSC, okay. A little bit different with Dr. Noli, okay, because he used directly the factor safety is equal to NS times C over gamma H, if I'm not mistaken. Okay. Based on Dr. Noli, she used directly the equation, this equation to get the factor safety. Okay. But from Dr. Kamaruddin, okay, he used the stability number, and from the number he get the CR. Okay, from the CR, he used the factor safety C is equal to C over CR. Okay. Okay, we look for the example. Okay, using the Taylor chart, determine the factor safety of the slope shown in figure 1. Okay, first phi is equal to 0 and then phi is equal to 20. Assume the hard stratum is far below the crest. Okay, this is clear. You already mentioned here far, not been stated here well below the slope. Okay, little bit confusing here. Okay, so far below the crest of the slope. So if far, so we can assume doesn't have any ND value. Okay, or the ND value is equal to infinity. Okay. But the ND is related to phi is equal to 0 only. It's not doesn't relate to the phi if the greater than 0. Okay. So for the first case, okay, this is the C is equal to phi soil slope. Okay, because in Taylor, okay, he has proposed two type of chart. Okay, for the first C, only for the C, okay, chart, while the other one is C and phi soil slope. Okay, so for this case, we have a C and also the phi. Okay, so we need to use the chart which is content of C and phi. Okay, so those it require trial and error procedure to determine the factor of safety. Okay, so to begin with, factor safety is equal to 1. Okay, in this case, due to the phi is equal to 0, okay, definitely the phi r also will become 0. Okay, for example, if we increase the value of the factor safety, for example 2, okay, at the end the phi r is also will become 0. Okay, so when the phi r is become to 0, then we check for the stability of the number for this case, okay, by referring to the Taylor chart. Okay, so this is a Taylor chart, okay, with the beta is equal to what we call as a degree of the slope. Okay, and then the phi r in this case we may use to get the value for the stability number. Okay, so when we use this chart, okay, actually this chart has been reproduced again. Okay, the value of the stability number is not a little bit less. Okay, because it's been reproduced again. Okay, so a little bit less. Okay, for example, in this example, okay, the stability number for this case is equal to 0.19. Okay, with the beta is equal to 60. Okay, let me yeah, let us check. Okay, beta is equal to 60. Okay, and then the step when the phi r is equal to 0. Okay, so in this case we obtain, okay, the value of the stability number is around 0.20 something, or say a little bit high, 0.20 something. Okay, while in this example the value is equal to 0.19. Okay. So but we refer to this number, okay, 0.19. Okay, so in your assignment or in your test or in your project, okay, so you may refer to the provided what we call as the design chart. Okay, sorry, the provided the Taylor chart. Okay, so 0.19 times 17 times 8, so the CI is equal to 25.84. Okay, so then we continue to obtain the FSC value. Okay, with the C is equal to 22. Okay, so 22 divided with 25.84, it becomes 0.85. Okay, so because the phi is equal to 0, okay, so no need for us to increase the stability, increase the factor safety value for the FS phi, because it will become 0 as well. Okay, so means that the phi r will become 0. Okay, so then, okay, we can conclude that the slope fail as the factor safety is less than 1. Okay. So that is for the first example. Okay, so now for the second example, with the phi is equal to 20, okay, the factor safety of phi is equal to 1 to begin with. Okay, so then we obtain the phi r is equal to 20. Okay, so by using the Taylor chart, okay, when the phi r is equal to 20, it is found that the ns of every number is equal to 0.095. Okay, determine the mobilized coefficient CR where ns then CR is equal to 12.92. Okay, 22 over 12.92, it become 1.7. Okay, so then due to the factor safety of P is not equal with the factor safety of C, okay, 1 is not equal to 1.7, then continue, okay, by increase the value of the factor safety of P and get the factor safety of C, okay. So the factor safety of P is equal to 1, FSC is equal to 1.7, FSV is equal to 1.5, FSC equal to 1.35, FSC equal to 2, and the FSC is equal to 1.22. So at the end, this is the relationship between FSC and FSP. Okay. So from there, draw the what we call line of equality. Okay. Then obtain the intersection between line of equality and the relationship is equal to the factor safety, which is 1.4. Okay. So that is for the Taylor chart. Okay. 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 Oh, sorry. Okay. Okay. So now, then we move to method of slices. Okay. We try to explain based on the slide first, and then we go for the example later on. Okay. Before, yeah, after we finish, after I finish in the slide, so we will take a rest. Okay. So method of slices, in this method, the potential failure surface is assumed to be a circular arch with center O and radius R. Okay. So the soil mass ABC above the soil mass ABCD above the failure surface AC is divided by vertical plane into a series of slice of width. Sorry? Into a series of slice of width B. Okay, the base of each slice is assumed to be a straight line. For any slice, the inclination of the base to the horizontal line is alpha, and the height of the measure at the center line is h. Okay. Okay, so this example of what we call as a method of slices approach. Okay. Okay. So the most important things, okay, that we need to consider, okay. For example, okay, if we have a 2-layer of soil, okay, for example here, okay, okay. So if we have a layer of soil, okay, so we need to make sure that the soil properties at the failure surface, okay, should represent one type of soil only. Okay. So for example, for this case, okay, 9/9 consists of one soil number A or soil number 1. Okay. While the slice from 1 to 8, okay, the base only cover with soil number 2. Okay. Okay. It will be wrong. Okay. Sorry. Okay. So for example, if layer of soil, okay, and for the slice number 8, it cover a portion of soil number 1 and the other portion of soil number 2. Okay, so we need to make sure that the base for the failure surface, okay, only cover with one type of soil. Okay, so another thing is, okay, so for example, for the slice number 6, okay, so we need to determine the center of the slice. Okay, for example, B divide with 2. Okay, so we gain the center line. Okay, at the center, the half of the width. So then we draw a center line. Okay, okay, so this center line represent the H. Okay, so why is very important? Okay, because when we want to determine the weight of the slice, so we need to multiply the unit weight with with B and also with H. Okay, so we may not use we may use the average H, which is the center of the slice. Okay, and the last thing is, okay, to determine the alpha. Okay, so alpha will be used, okay, to determine the length of the slice at the base. Okay, so in order to determine the alpha, okay, so for example, for this line, this red line, okay, so we need to extend this red line, okay, and then this center line, okay, should extend as well. Okay, so by the use of the protector, okay, so we need to determine the degree of the alpha. Okay, so this alpha will be used in the equation, okay, to obtain the length of the base, okay, which is under the resisting moment. Okay, so the same concept with the total stress, okay, where we use the moment concept. Okay, but we need to calculate for each slices. Okay, for example, slice number 1, you get the value slice number 2 until the slice number 6. Okay, so the most important thing is to determine the alpha. Okay, and the alpha also depends on the location from the center. Okay, for example, if the alpha is on the right side of from the center, okay, so we consider it is a positive. If the alpha is on the left side from the center, so we consider as the negative. Okay, or if we want to use the right side as a negative, so the left side should be positive. For example, for this case, okay, this is alpha is on the positive. Okay, let's say for the 2, okay, so then we draw a straight line from the center, okay, and then draw a center of the side number 2. So then we obtain the alpha. So the alpha is on the left side of from the center. So the alpha will become negative, and also with number 1 also will become negative. And start from 3 to the number 9, so it become positive. Okay. So the best way to solve the problem by using the method of slices is to plot on a grid paper or graph paper. Okay, because it will be easy for us to determine the H, B, okay, and also to get the value for the alpha. Okay. Okay, this example of the force acting on the each slice. For example, there is a side force, okay, which is the X considered as a shear force acting on the side of the slice. Okay, and then they have a E, which is a normal stress acting on the side of the slice. Okay. So on the what we call on the base of the force, on the base on the slice, okay. So there will be a shear force as well, which is considered as the resisting force acting on the base, and also they have a normal force, okay, which is acting on the uh, per, uh, perpendicular to the base. Okay. So based on the side force, okay, there are several assumptions been made by several researchers. Okay. So for example, okay, for original method of slices, okay. So the author has considered or assumed the S and E is equal to 0, and also there are no pore water pressure. Okay. So then they derive the equation. Okay. Then another assumption made by Philenis, okay, where they assume the S and E is equal to 0, but they include the phi value. Okay. Then they come up with the equation that consists of seepage or phi value. Okay. And for our discussion later, okay, the modified Bishop, okay, has considered the side force effect, which is X and E, okay, and also consider the phi value, the pore water pressure, okay, and then he come up with another equations. Okay, so we may learn 3 types of equation, okay, for the method of under the method of slices. Okay. Okay. So this is a common equation, tau f over tau m. Okay. So this is the one that I have discussed previously. Okay. So I have explained on the x, on the e and the x. Okay. On the weight, okay, to get the gamma time bh. Okay. Okay, so any external force must be included in the analysis, but we need to make sure that the force has been should have same units. So for example, if it is considered as moment, so we need to use the same unit of moment. Okay. Okay. So this is the derivation. Okay, for a normal, what we call as an ordinary method of slices, which is doesn't have any pore water pressure. Okay. Then the Philenis include the pore water pressure, okay, in the equation. Okay, then Bishop. Okay, Bishop has assume the effect of force on the side of each slice I accounted for to the some degree. Okay. And also include the pore water pressure. Okay. So later on, this is the kind of force polygon, okay, for under the Bishop. Okay. So we only consider on the vertical, what we call vertical force, not the horizontal for the delta P. Okay. From there, they derive the equation. Okay. However, for the Bishop, is very tedious method. Okay. Because we have a factor safety on the left and also factor safety on the right. Okay. For example, for this case, this is a factor safety on the left, while this is a factor safety on the right. Okay. So we need to assume the factor safety on the left, on the right first, and then we may obtain the factor safety on the left. Okay. So we start first with this one, okay, and then we may get the factor safety on the left. Okay. So if the factor safety on the left, on the right is not equal with the factor safety on the left, so we need to repeat, okay, at least for 3 attempts. Okay. So at the end, we need to plot for the relationship and then use the line of equality. Okay. Okay. So this is the MA, okay, which is the okay, so this is the MA, okay, because the actually the equation is very long, okay, so it has been simplified, okay, by putting the 1 over MA. So actually this is the equation, okay. So then it's been simplified into 1 over MA, then become this MA. So we may separate calculate for the MA, okay. Or we may use this kind of approach, okay, but I'm not very familiar. Okay, later, for me, it's better just to calculate the all of the equation by assuming first the factor safety on the right, and then we obtain the MA. So from the MA, we just solve the problems and then get the factor safety. Okay. So this is this is the example that can be used to estimate the MA. Okay. So it depends on the alpha value. Okay. So from the alpha value, we can get the we refer to the what we call as the this tangent phi over f. Okay, by assuming f as certain value, so then we can get the MA. Then put the MA in the same equation, and then we obtain the Fs. If the Fs is not equal with the F that we assume in this equation, so repeat again. Okay. So assume F right is equal to 1, phi MA, M alpha, which is MA. Okay. Then find F left. Okay. Take the average of the F right and F left. Use the average F, find the M and gamma and alpha. Then repeat until is small enough, which is 0.01. Okay. Okay, due to repetitive nature of the calculation and the need to select the most critical failure surface, the method of slices is in particularly suitable for solution by computer. So this is the lesson. Okay. So at the end, we may use the software. Okay. So more complex geometry and source strata can be introduced. There are another method of slices as shown in the following table. This method use a different assumption on inter-slice force. Okay. So later on, you may use the software. For example, the common software for the what we call for the slope is GeoStudio. Okay. So GeoStudio, we have a limit equilibrium method, which is under the slope W. Okay, we also have they also have a finite element approach, okay, which is the sigma, okay, and also the SIP, okay, where SIP can be used, okay, to determine to include the water or any unsaturated condition or suction, okay, for the SIP. And for the sigma, it is developed to determine the deformations, okay, which is under the finite element. While for the GeoStudio, for the slope W is to get the factor safety value. Okay, so we can do a couple analysis, meaning that we can start with the SIP and then we can run for the slope W, or we can run for the sigma and then we run for the slope W. Okay, so this is several type of what we call as of the methods under the method of slices. Okay. Ordinary method, okay, Bishop, Jumbo, Morgenstern Price, Spencer method. So they keep improve or evolve. Okay. So for our part, we may learn on Filianis and Bishop methods. Okay. Okay. We will discuss based on example. Okay. So we should have a rest for 10 minutes.